So in this mini lecture, which is the third in a series of lectures on Factorial ANOVA, I'm going to be talking through all of the steps to actually conduct a Factorial ANOVA through the assumptions and the main analyses and look a little bit at SPSS results. So the first thing you want to look at in assumptions is, of course, missing data. So any data set you have, you always want to go in and look at missing data, see if there's anything that can be estimated, or maybe replace a missing question here and there with the case-wise mean. Second, you'll want to look at equal group sizes. In a two-way, three-way, or more ANOVA, that's going to be more complex than it would be in a simple one-way ANOVA. A one-way ANOVA, you may just be comparing like men and women and see how many are in each group. But if you have a two-way, as you can see on this picture, this is a sample. Say there's 45 people in this study, and you've got 25 men and 20 women, as you can see there. So that's not too bad. It's close. And then you're also giving people two different types of therapy there. Okay, so cognitive behavioral therapy and emotion-focused therapy. And you have 24 people that ended up in the CBT group and 21 people that ended up in the EFT group. That's not too bad also. But you also need to look at each individual group. So how many men ended up in CBT, how many men in EFT, how many women in CBT, how many women in EFT. Again, all these numbers don't look too bad. That 9 there of women in CBT is a little low, right? Like starting to kind of push it in terms of, you know, all of your analyses that you are doing in this means there's only 9 people in that little cell that you're looking at when you look at women who got CBT. So that's kind of small. And this also shows that Factorial ANOVAs usually do need a little bit larger sample. I think you usually like to see at least 20 people in each cell to do your analysis, particularly if you're wanting to do interaction effects, which are those 4 little ones there, the 15, 10, 9, and 11. Those are going to be your interaction effects later. And so those are pretty small, and you're starting to get questions about whether that's enough people. Even unevenness is a little bit uneven too. Sorry about that. 0.182, so that's not significant, which means we've passed the assumption. So in this case, Levine's test is passed. Happy for that. So even though we have unequal n, at least we have homogeneity of variance. So that's great for you going forward. Since those two assumptions, remember, they kind of go together. They're like cousins who like to hang out. And, you know, if one goes bad, at least one of them maybe will keep from going bad as well. But if they both go bad, meaning homogeneity of variance is violated and unequal n is violated, then, you know, the whole study is questionable now at this point. So one of the other things you might want to look at is to see whether you think there might be a factor interaction before you even run your ANOVA, to see whether you're going to do some of the extra steps and work to understand the interaction effect. So you can do that by just running a line plot and graphs and see if you get something that looks like the example that I showed you earlier about assumptions. Okay. So remember, we're going to have 3 F-tests in even just a two-way ANOVA. So I'm going to kind of walk us through a two-way ANOVA here. So when you run SPSS, it's going to give you everything all at one time, right? And it's not going to necessarily put it in the order that you're supposed to look at. So remember, the interaction is where the action is. So you're going to look at the F-test for the interaction first. And if that's significant, then you're going to need to look at something called simple effects, which is essentially each of those individual little groups. You know, the men who got CBT compared to the men who got EFT, compared to the women who got CBT, compared to the women who got EFT, and compare those all to each other in those little groups, all right? So that's one avenue that you need to go down. After you finish that avenue, then you need to go back and you need to test the main effects for just therapy, right? And see if that F-test is significant. And then you can compare those with a post hoc, maybe a Bonferroni, a Tukey, or Sheffe, just to see. Of course, if you only have 2 groups, you don't need to do a post hoc comparison. You just look at the 2 mean scores and see which one is higher. But if you have, you know, 3 or more groups, you're going to have to run some kind of post hoc comparison for the main effects. And then don't forget your other independent variable. So in my example, that would be gender. So you have gender as one independent variable. You need to compare that all on its own, and then therapy as another variable. So you're running 3 F-tests and the follow-ups for each of those F-tests. So I'm going to show you that on SPSS output now. This is the primary thing you want to be looking at. And so you'll notice here that we've got an F test for interaction we need to look at first, right? So here's your degrees of freedom that you need to look at there, circled on the left, and then circled on the right, you've got an F of 1.15 and a significance of 0.33 for the interaction. So our interaction is not significant, right? And so you'll see down here, this is actually a 2x8 ANOVA, which is ridiculous, but just to let you see it. And you can see how I wrote it out here. This is what it would look like if you write it. And then after looking at the interaction, now we're going to look at the main effect. So the main effect of sex or gender there is 15.57. That's significant, p less than 0.001. And the partial eta squared of about a 0.02. And then the work status one also has an F value that is significant. So it's 2.63. And its significance of 0.0 equals 0.01, and a partial eta squared of about 0.02 also. So if your interaction, in our example, the interaction was not significant, so you wouldn't look at this table. But if it had been significant, then you would look at this table to help you guide your decision making about what is significantly different than what. So as you can see in this table, you've got like the two, remember it's a 2x8. So you've got the two groups, males and females, and then you've got the 8 groups of different labor force status right there. And you can see the mean scores for all of them. So it gives you a chance to just kind of look it over. You actually don't get a very good way of comparing the groups. You can use confidence intervals. Sometimes people do that, and I'll show you how to do that in the lab. But there's a better way. I just want to introduce it. And this is the website, and I'll put the link also on the in Blackboard for my students. But IBM, which is the SPSS, owners and creators, this involves actually changing the syntax in the SPSS computer. So basically going in and altering the computer language that runs it to do something complicated that it can't do with just a Windows push a button kind of thing. It's a little bit complex, so I'm going to show it to people in the lab, but I want to make sure people are aware of what that is. And then this is the result that you get. And you can kind of see here, this one I did instead of 2x8, which is just way confusing, I did a 2x2 where people are either continue or stop working if they were rich, and then male, female. So it's a different study. And you'll see everything is significant. If you look at the SIG, column there where it says SIG, SIG, then you can see, okay, continue working, male, female, that's significantly different, than everything else. And so you can kind of go through and just see if those mean differences are significant. And this is at the 0.05 level. So this is where if you had to adjust your Bonferroni, here you'd be fine because the significance are all less than 0.001 on this particular one. So this is what that looks like. If you change the syntax, you're going to get this. If you don't change the syntax, you will not get this table. That requires the syntax work. And this is the other thing that you can get in a pairwise comparison. So this is if you have just gender, say the independent variable of gender is significant. And in this sample, we only have 2 groups. So you just can report the mean scores. Yeah, males had higher scores than females. Very small difference, but it's significant according to our analysis. So, okay. 1.38 versus 1.32. In fact, you could just report, working full-time participants were significantly different than retired participants, right? And you could report the mean scores. And, P equals 0.007, and, you're done at least with that group. But it can end up where you have like half of them are significant maybe and half aren't, and then it gets kind of complicated. What a lot of people do when that gets complicated, when they're actually presenting data, say on a midterm exam with me or a final exam or things like that, is they'll go in and just kind of make a table and put the table in and have all the mean scores, and they might like put a star next to everything that's significant, or maybe just present only the ones that are significant mean scores for those. So you're going to have to make some choices about how you want to report data when it gets complicated. But I hope that this gives you a little freedom of how you want to do that rather than kind of listing everything out. Also, in my own class, I don't mind people doing bullets instead of paragraphs when they write up results sections later. So you guys will be doing that in the midterm and the final for me. And, bullets are really helpful. So Okay, that's everything about ANOVA.